Hey everybody, welcome back. We've talked about conservation of linear and angular momentums. Today let's talk about the third and final of the conservation laws, conservation of energy. Really what we're saying with conservation of energy is we have some system and we're going to write an expression for the total energy of the system. Recall that, cat hair. What this law is going to tell us is that if you are able to write an expression for energy of the system at a certain moment in time, and if you were able to justify application of this law, if the system meets certain conditions, then the energy of the system at time 1 will equal the energy of the system at time number 2. And when we talk about the energy of the system, we mean the total energy, which we've talked about. Total energy means kinetic plus potential. Now, how can we use this, or how do we justify this expression that the energy of the system doesn't change? Well, really what we can do is we can talk about what would cause the energy of the system to change, the total energy of the system. So we know that, for example, you can have objects falling under gravity, right? And it would have velocity at time number 1. And then here it is again, and it has a velocity at time number 2. And clearly these velocities would not equal each other. Terminal velocity, something like that. But let's just say an object in free fall. You can have the case where the object is accelerating, right, through some potential field, which means there is a transfer of potential energy to kinetic energy. Okay. Notice that in this case, this law would still apply, right? If you just have an object moving through a potential field, the energy of the system does remain constant. Now, what then would cause this to not be true? What kind of situations would cause the energy to change? What if you have your object, and we'll just use a block on a table, and instead of being accelerated through some potential field, what if instead this object just has a force applied, some external force? This external force, unless we have some other kind of declaration about it, this external force has no potential energy associated with it. Gravity is it's a certain type of force, and I'm gonna lay out some jargon in a bit. But gravity is a conserved force, which means you can transition between the existence of a gravitational potential and then the kinetic energy created by the acceleration of gravity. In this case, if you just have a block on a surface, this force is going to cause the block to accelerate, and it's going to give the block some kinetic energy or change in kinetic energy. And unless you're able to define a potential associated with that force, then the energy is going to change, right? The energy of the system. So I'm going to characterize this case, let's say number 1, and what I'm about to list, I'm about to say things that make energy break, things that change energy. Okay, something like that. So the things that would make it so you can't use this law. Number 1, some condition like this where you have an external force. That would be one case. And then the second one we actually touched on just a moment ago when we were talking about gravity. The second one is friction. So here's an object. I can take this object and I can put it on the surface and I can give it a little push, right? And it doesn't go very far because I didn't push it very hard, but also there is friction with the surface, and that friction is going to dissipate the kinetic energy inside of this eraser. So these two cases, these are going to cause the total energy of the system to change, and we can actually group these two together. I'm going to give them a name, and that name is non-conservative forces. So these are non-conservative forces. What would be a conservative force? Well, gravity would be a conservative force, because you can have an object at a height, you can let it accelerate through gravity, and then you can still total the kinetic energy and the potential associated with gravity, and you get the same quantity. What are some other conservative forces? Springs. Springs would be a conservative force, right? Because we have a potential associated with the spring. So if you look through your problem and somewhere in your problem you have an external force, or if you were applying friction, then this is immediately not true, right? And you still, right, we might still be interested in the energy of the system, but as far as a conservation law, then we cannot apply it. Okay, I've got a little bit of comments left to do on this one, so let me clean this up. A couple of theoretical comments left, and then we're going to do a small example. So what about systems with non-conservative forces? Which is to say, really, any real-world system, right? Because a non-conservative force like friction, well, clearly there's friction basically everywhere. So we can't apply conservation of energy to this problem, but what we can do is we can say that the energy of the system is equal to, and we know that this is going to be kinetic plus potential, and then is there some way to consider the effects of non-conservative forces, things like external forces or friction? Remember that we have talked about the quantity work. We said that work is equal to F dP integrated. You could also formulate this as a function of time. We could say that if you take force and you dot it against velocity, for example, that would give you the change in work, and we could find work by integrating both of these, right? That'll still give us work. Okay. So what you can do is you could take all of your non-conservative forces, things like friction, actuators, motors, things like that, and you can calculate the work done on that system by those non-conservative forces, and then take them and then add them to this equation. Now, when you add them to this equation, you do have to be mindful about signs. Say that we have a box on a lower ledge, and we do some work on the system, and we move that box to a higher position, which means we just gave it some potential energy. The work that was done on this system, let's say I do the work on this system, that means I have added energy to this system, right? And clearly I did, because I moved it up. So I lost a little bit of energy, and the box gained a bit of energy. When you add work to this equation, it's negative, which is just to say that, let's say that we were performing this analysis for the box, and we had this claim about energy at two different moments in time. So at time 1, kinetic energy is equal to 0, potential is equal to 0, and no work has been done on the system. So these numbers, this is for time number 1. Now at time number 2, the block is still not moving. That's fine. Kinetic energy is equal to 0. And at this time, let's say the potential is equal to 10. Well, if the potential is equal to 10, then I can assure you that the work is also equal to 10. And if this is 10 and we're subtracting 10, then the energy is equal to 0. In this case, what we have done by adding the work is we're not so much looking at the total energy of the system. What we're doing is we're checking for energetic consistency. If this was an experiment, or if this was simulation, and you had access to instantaneous kinetic, instantaneous potential, and this, remember, work is an integral. So you're integrating it as you go along, and we have access to the total. If you have all of these terms, and you arrange them as such, T plus phi minus the work done, then this quantity on the left should be, and I'm going to put an approximate, it should be approximately 0. Now, theoretically, it's exactly 0, right? The energy came from somewhere, and the energy went somewhere, and it's not being created, and it's not being destroyed. The reason I say that this is approximately equal to 0, at least in simulation, if you haven't made it into your programming classes, or if you're not particularly familiar with numerical methods, that's okay. You will be. But anytime you do a numerical process, so numerical integration, simulation, something like that, because it is numerical, it's not exact. So this will come out to be 10 to the negative 12th, something small, depending on your thresholds. And what we have effectively done by adding work is, again, we've just made some kind of energy check. This is a good way to check your system if you're performing some kind of simulation and you want to confirm that your math is correct. If you screw your math up somewhere, perhaps when you look at the results, you don't know that they're wrong. But if you go back and you look at your energy quantities, mistakes in the dynamics, they usually crop up very quickly when you go to calculate energy. Okay, let me clean this up and we're going to do a brief example now. For our example for conservation of energy, let's talk about objects in space. Now, why objects in space? Because remember, we can't have any non-conservative forces. So there can't be anything external, no motors, no actuators, and there also can't be friction. So objects in space is an ideal setting, right? An ideal problem to look at. So let's say that we have a rocket ship full of toys that is traveling from Earth to Mars. And somewhere along the way, there's a problem and they have to dump their cargo. So we end up with all this space debris. We have bicycles in space. We have Xboxes and PlayStations, right? They're just out there floating. And along with them, we have some slinkies. Now, if you're not familiar with the slinky, I'm very old. I remember these. They were springs that you would give to kids, and you'd let the kid play with the spring, because that's how it was in the past, in the old days. So what we're going to do is we're going to look at the behavior of this slinky, this spring, inside of or in space, and we're going to model it as a mass connected to another mass. And I'm going to let me clean that up a little so you can see what I'm doing. There we go. And I'm going to put K between them. Now, in actuality, if you took a slinky, you took a spring out to space and you started moving it, the material inside of that slinky and that spring, the material itself is deforming. And there's going to be some internal friction associated with that deformation. We're going to pretend that doesn't exist. We're going to talk about how to model those. In a future video, we're going to do springs, and these are masses, and we're also going to include dampers. If you have those three together, then you have a spring, mass, damper system. So what we're looking at is we're going to look at a spring mass system, so no friction. And then this is how we're going to model it. I know this is a little simpler than this kind of continuous spring, but I for now this will do okay. So we want to first consider, is conservation of energy applicable? Can we even apply it? And again, that just goes back to non-conservative forces. If you can show that there's no non-conservative forces, feel free to apply conservation of energy. Whether or not it's useful to solving your problem, okay, that's up for debate. But in this problem, we're going to use the energy at time number 1 is equal to the energy at time number 2, and we're going to see what all claims can come out of this expression. So we need to build up to this, and clearly energy of the system is going to be kinetic energy and potential energy. All right. So which of these quantities exist in our system? Well, we have two masses, and let's call one of them body A. We can call the other body B. Each of these will have kinetic energy. Now, what kind of kinetic energy will they have? In a very general case, your slinky can be spinning about all three axes, right? It's going to be translating. We're going to say that it's translating in 3 dimensions, and it's also rotating in 3 dimensions. So we need to talk about degrees of freedom and rotations, etc. but there will be kinetic energy of A and there will be kinetic energy of B. And then what about potential energy? We could, for example, we could talk about the gravity of Mars pulling on our slinky, the gravity of the Earth, the gravity of the Sun. Let's not worry about that, right? Let's just say that here for T, we've got TA and we've got TB. And for potential, let's say that there is the potential of the spring. Okay, so there's our problem set up. We're all in agreement that these quantities exist, and since there are no non-conservative forces, this total will be the same. The kinetic energies, what are these functions of? Kinetic energies are going to be functions of things like Q dot and theta dot, and the spring is going to be a function of Q. And of course Q, we're going to go through and we'll mark up the diagram and everything, but Q is going to be the displacement between these. The potential associated with the spring has nothing to do with how fast it's moving. It's purely a function of position. Okay, let me clean this up a bit and we'll roll through the write-up and we'll get started. Let's do the write-up for the problem. Here's our two bodies, A and B. We know that we need some point N. How complicated do we want to make this? We know that in reality, this slinky could be, spinning all over the place. We're going to keep it to the planar problem. Let's say that the system is rotating, and I'm just going to write it as a theta dot on the diagram. So the system itself is rotating, and then there is some extension between these, and I'm going to call that Q. Now, let's say that we're not worried about three-dimensional position vectors, so we can start writing some of these. Let's say that the position vector from N, and when I say to A, let's put in some centers of mass, that's fine, A and B. P into A, let's call this one Q1 X hat N and Q2 Y hat N. P A to B, what is P A to B gonna be? Well, we need some frames on this. Obviously, we need an inertial frame, and then let's put the A frame and the B frame aligned like this. So the let's do this. Let's say X A is pointed like that. And the A frame and the B frame, they're aligned together. There's also, I'm not going to say there's any rotation of the B frame, no rotation of body B. All it does is it slides back and forth in line with A, and the spring just compresses. Okay, so the position vector from A to B, we have this displacement Q, and that's going to be in the X hat A direction. And of course, there is some little geometric offsets between these. So I'm just going to write that as some delta, some number in the X hat A, and we're going to say that delta is a constant. It represents these offsets between the centers of mass. That's all. Okay, what else would we need to do? Obviously, if you're doing the write-up, you need to define your rotations, and we're going to say that these two are equal to each other. They rotate together. What else? Constraints and degrees of freedom. Is there a constraint on this problem? You might be tempted to say that the spring is a constraint, but understand, I can hold A in place, and I can grab block B and move it back and forth, right? And the spring will produce a force depending on the position, but the spring does not prevent me from moving it back and forth. So the spring is not a constraint. So there are no constraints. How many degrees of freedom then? Well, we have, just from our setup, we have Q1 and Q2 tracking the center of A. We have this is now Q3, following the displacement of B. There's another one, and then we also have this angle theta, representing the rotations. So there's the angle theta as well. So this problem is going to have 4 degrees of freedom. Body A can move in 2 dimensions, it can spin, and then block B is going to be in line with A. It's just going to be a translating distance. So in total, we will have 4 degrees of freedom. Okay, what else can we call out right now? We can do angular velocities. We can say that omega into A is equal to omega into B, and this is theta dot z hat A. We can also call out velocities. So the velocity, linear velocity of A is very simple. You just take ddt of this bit. So we're going to have q1 dot x hat n and q2 dot y hat n. What about the velocity of B? So velocity of B, ddt of P in B. Now I do not have P and B written, but it's of course just the addition of these two. So we've already taken ddt of P and A, and that's VA. So I can say that this is equal to VA, and it's going to be VA plus something. So the plus something is ddt of the second piece now. We've got PAB, right? And we need to take ddt of this quantity. And what's going to happen? Well, we have the scalar Q3, which is changing. So we have Q3 dot, that's in the x hat A. And then we have x hat A also changing, right? And we have this x hat A changing, and we have that x hat A changing. We know how to take derivatives of moving frames. We're going to use transport theorem. So this will come out to be Q3 plus that little number delta multiplied by theta dot ZA. And there's your transport theorem for this one. Okay. All right. So we have all of this. What was it we wanted to talk about for this problem? We wanted to talk about the energy, right? We want to apply conservation of energy to this. So now all we need to do is we need to list out the kinetic energy of A and B, and then we need to write an expression for the potential of phi, and then we'll talk about the usefulness of that equation. Which one of these are easy? I'm going to say that phi is pretty easy. I'll do it down here in the bottom. Phi of the spring. Now you should have an equation for this one. The equation for potential energy of a spring is 1/2 K multiplied by the displacement squared. So what is the displacement of this? Well, we're tracking the displacement with Q3. But remember, we're modeling a slinky, right? And slinkies have some unloaded length. So what you can do is you can just find the change in that length. So I take the current value of Q3 and I subtract the original unloaded length, and then we square that quantity. It's 1/2. I tend to think of potential of spring as 1/2 kx squared, something like that. You just have to remember that this is a delta, right? Okay. Another quick point, just because this is squared, right, it actually doesn't matter the order here. All we care about is the change. The sign is irrelevant. So we've got potential of the spring already taken care of. Let me clean this up a bit, and we'll do the kinetic energies. Kinetic energy of A, TA. We've done this several times. We know these equations. 1/2 V dot K, and since this is A, we're talking about VAKA. Plus 1/2 omega NA dot HAA. And of course, momentums. We know how to define the momentums. So the specifics in this one, what would it be? TA is going to equal 1/2. I tend to think of these as vectors, so I will write them as vectors for now. And here's VA. It's all in the N frame. We have Q1 dot, we have Q2 dot, and we have 0. This is going to be dotted against MA and this same vector, Q1 dot, Q2 dot, and 0. and then it is plus the 1/2 omega is theta dot ZA, and it's going to be dotted. HAA, we've done this several times. HAA is IAA omega NA, and if you perform that calculation, what kind of assumptions are we going to make? We're going to say that these theoretical masses are axisymmetric bodies, right? So the off-diagonal terms are 0. There are only terms about the diagonal. And of course, you can do that expansion. You'll see that, let's see, we're going around the Z. So this is the IZZ, AA, theta dot ZA. Okay, I'm gonna leave VB down on bottom just to help us out in a minute. And if we perform all of these expansions, what are we gonna get? Well, there's a 1/2 in front of all of it. And then we'll have, remember on the dot products, you need to perform the multiplication of terms first, and then you add all of those together. So it's kind of a sum of squares. We're going to have Q1 dot squared plus Q2 dot squared. And then of course I've got MA and the 1/2 out front. And I'm going to drop down to do the rest of this. We will have IZZ AA theta dot squared. I'm going to close the brackets. It's a scalar. We had vectors here, and then we dot products, so there's we lost those terms. So this would be the kinetic energy of A. What about the kinetic energy of B? B is slightly more complicated. Here's the velocity of B. Notice that B is VA, here's VA, plus, and now there's some terms in the A frame, right? Oh, and this one, whoops. Fix this in your notes. This is YA. Okay, that's fine. VB is this. So we have the original VA that's in the inertial frame, and then we have some additional terms that are in the A frame. That just means we have to put it all in the N frame in order to perform the dot product. What about the second half? Well, body B is rotating with body A, so then it's just about inertia. And if we're making the assumption, right? We're the one modeling this slinky as a couple of masses. We would probably choose for these inertias to be the same. Maybe not, but for now, we just pretend. Okay, so you've got TA written down. Let's talk about then VB now. And I'm gonna put this all in the inertial frame. So we had Q1 dot, X hat in, we had Q2 dot, Y hat in, we had Q3 dot, and this is going to be cosine theta X in, sine theta Y in, and then we also have, it was Q3 plus delta, and that was Y hat in, so that is negative sine theta X in plus cosine theta Y in. What is VB dot VB? Well, you're going to have the X terms, all of the X terms multiplied together. So this does get a little more complicated. That's okay. It's going to be Q1 dot plus Q3 dot cosine theta squared plus, now the Y hat in terms, or sorry, there's a, ooh, okay, sorry, I left one off, plus, let's change these parentheses to some brackets, plus Q3 plus delta multiplied by negative sine theta. There we go. And it's that quantity squared. This is just the X hat ends, right? This is just the X hat in terms. All of this is the X hat in right? And because we're performing the dot product, they all get multiplied by together. So it's this whole quantity squared. And then we're just going to, we're going to bring down the y hat in terms. And there's, you know, similarities here. So Q2 dot, right? There's that first one. The next one is Q3 dot sine theta. And then the last one is Q3 plus the delta. And this is now cosine theta squared. So this would be your VB dot VB, which of course goes inside of your energy expression for B, which we can just swap out some of these letters, and it'll take care of it for us. So the kinetic energy of B is VB dot KB omega into B dot HBB. All right. So you can go through and you can do all these details, right? And at the end of it, you're going to end up with some expression that has all of this stuff in it. So let me clean this up just a little bit, right? And we'll look at that whole expression. I've gone ahead and written all of the terms in the energy of the system. Quick comment, I did leave the theta dots off of those before, just make sure you have it in your notes. So we said that this first one, this was phi of the spring. These first two terms, these are the kinetic energies of A, and then the next two terms, these were the kinetic energies of B. Okay, and again, the original claim was that since we're modeling this slinky in space and we're pretending there's no internal friction, we can say that the energy at some moment in time is equal to the energy at another moment in time. So you take all of this, and this becomes the left-hand side when all of the changing quantities, remember we said the system had 4 degrees of freedom, and the quantities, the generalized coordinates were Q1, Q2, Q3, and theta. So all of those quantities, when you take all of these quantities at time number 1, that includes their speeds, Q1 dot at time number 1, Q3 at time 1, Q3 dot at time number 1, right? Everything at time number 1 on the left-hand side, and then everything at time number 2 on the right-hand side. Some of these things are constants. The mass, the inertia, this little geometric delta, these are all constants. We're going to pretend that the spring constant is constant. It actually isn't. All springs are nonlinear, but pretending. And then everything else is variable, right? All of this other stuff is variable. So we only have the one equation. This is a scalar equation, and this that I've written, this is scalar. So in all of this, we can only solve for one thing, which means suppose the question is at a certain moment in the future, how fast is the system rotating? Which means we want, there you are, we want theta dot. And theta dot is right there. But theta dot is also right here. And theta dot is also right here. You can see that it becomes very difficult then to solve explicitly for theta dot. It's clearly quadratic, right? So we would have to cast this whole problem using a quadratic equation. Let's say that the problem is asking for how fast is this spring vibrating, right? Which means we're really looking for the value of Q3 dot. Where in here is Q3 dot? Well, Q3 dot is right there. And yeah, okay. So we've got these two Q3 dots. Good. Just checking. Q3 dot should not have been in the kinetic energy of A, so only in the kinetic energy of B. Also not in the potential. Okay. So we only got the Q3 dot. That's a slightly easier question to answer. That means you isolate the Q3 dot, you factor out the bits that you have to, and then you take everything else and you move it to the other side of the equation, whether through addition, subtraction, or division, right? And then in all of that, you can only solve for one thing. You can only solve for Q3 dot at time number 2. And what does it require? It requires that you have full knowledge of time number 1, and it requires that you know everything else about time number 2. I would have to specify Q1 dot and Q2 dot. I would need to specify theta dot at time number 2. And all of this would allow me to solve for a single variable, Q3 dots. Okay. This was conservation of energy. I mean, this is, all the conservation laws now. We've done linear momentum, angular momentum, and conservation of energy. All 3 of them are very situationally specific. They have requirements that you must prove in order to justify the application of that that conservation law. Which really just means they're not broadly applicable. We can use them for certain situations, but not many. Okay, I think this is it for the conservation of energy. Just just be careful using it. There's a lot of work involved, and you can only use it to solve certain stuff anyway. So yeah, that's it. Okay, y'all have a good day. I'll see you next time.